at a cell membrane, we're looking at the inside and outside of the cell. So we have the intracellular side here, that's the inside of the cell, extracellular side there, that's the outside. Those are full of mostly water. So because of that, glycerol right here and the glycerol on the inside, those things are polar and hydrophilic. They love water. They want to spend time with water, so they face themselves so they can be as close to water as they can. The hydrophobic parts are fatty acids. They hate water. Think about oil in water and butter in water. They repel each other. So our fatty acid tails assemble themselves sandwiched together so they can be protected by that water-loving hydrophilic glycerol layer. So it protects them from the icky water that they hate. They're hydrophobic, water-hating. The water-hating things are typically non-polar. So non-polar is hydrophobic. Polar is hydrophilic. And that's going to affect a lot of what can and can't pass through the cell membrane and how it does it. We'll talk about things, we'll get a little more specific about that in a second. Last three things. I think we did cholesterol, right? Mm-hmm. We did glycerol, fatty acid tails, phospholipids, but we haven't talked yet about membrane proteins, either integral membrane proteins or peripheral membrane proteins. The integral membrane proteins have another name. We can also call them transmembrane proteins. Just like a transcontinental flight goes all the way across the continent, New York to LA, a transmembrane protein is going to go from the outside of the cell all the way to the inside. So it touches both the outside and the inside, which is why it's a transmembrane protein. It goes the whole way across. Sometimes transmembrane proteins are also called carrier proteins. Now, we had the discussion on Friday about how a cell membrane is selectively permeable, kind of like a screen door. And screens will allow small things through like air, but will prevent large things from going in and out. But then we said, sometimes you can put a hole in that screen so larger things can pass at will. And the hole that we put in a screen was a dog door. So the dog can go in and out and in and out and in and out. That's what that carrier protein's job is. It serves as a larger hole in the membrane that allows things to pass in and out without tearing the membrane or destroying the membrane or making the hole larger. I mean, it's totally possible that if you wanted to go through a screen door, you could take a knife and cut it, right? But that destroys the screen. So it would be possible to get through this. You could go ahead and cut the cell membrane, but it's going to destroy it. So instead of doing that, we put a carrier protein in there, and that carrier protein allows things to pass in and out. It lets things that are bigger pass in and out, and it allows things that are polar to pass in and out.
So what's an integral membrane?
Integral is just another name for it.
Wait, so they look like smaller.
So everyone's going to have a different size, shape, and function based on what it is they let through. So if you let through a big molecule like urea, you're going to have to be really big. If you let through a small molecule like glucose, you're going to be smaller. Or if you let through something very small like an ion, you're going to be very small. So every transmembrane or integral protein has a different shape and different size based on the different thing it allows through. So in our example from Friday, if my sister had wanted a dog door for her basset hounds, it's going to have to be a larger hole in the screen than for one of those dogs.
Let's say it's like a big hole. What keeps like really small things from going into it?
The nature of the polarity. So what we don't realize is that this is some of them are called gated channels. So they have a gate on it and will only open for things of a specific shape. So remember that toy we talked about from childhood, how like the star goes in the star and the moon goes in the moon? It has to be the right shape to fit. Even if it's a big hole, if it's the wrong shape, it won't go through. It's chemically repelled. And some of them have gates, and they change shape. It's very strange. Peripheral proteins. Peripheral proteins are typically used for communication in cells. They're typically used for communication, and we call them peripheral because they occur only on one side. Just like your peripheral vision occurs only on the side, when we say peripheral, it only refers to the vision that's like right here that you can see out of the corner of your eye. Not this. This isn't your peripheral vision. This is. So peripheral proteins occur on only one side and do not span the whole membrane. And their function is entirely dependent upon what side of the membrane they're on and what protein they are. So they're so vastly different, we can't really sum it up other than saying some communication. Last thing here is like a ziggy-zag thing. Those are carbohydrates. Yep.
Are they grouped on their location and not their function?
They're actually all like throughout, so it's not like they only occur in one spot. They'll occur in anywhere in the membrane.
So then how do they group like the parts, like what they're called? If they all are so different.
We group them essentially, like peripheral is on their location, right? Like we can't say their function because we're like, well, they're just on the outside. Integral membrane proteins, pretty much we just say are mostly carrier proteins. So they also get narrowed to function as well as shape. Does that make sense?
Yeah.
All of those are carbohydrates, every last one of those zigzaggy things. You'll notice they're only on the outside of the cell. There are no carbohydrates on the inside of the cell. That's because it doesn't make any sense to wear a name tag inside your jacket or inside your sweater. When you put a name tag on, you put it on the outside so everyone who encounters you can see who you are. Carbohydrates are just a name tag for the cell. It's like saying, hello, my name is nerve cell. Please don't attack me. That's how your body knows how to respond to different cells that it encounters. Because if it reads that carbohydrate and is like, hey, that one doesn't belong here, it responds accordingly. So that's why it's only on the outside. That's essentially all of the parts of the cell membrane. Thank you, my dear. Oh, you need this in case they stop you when you're trying to walk out the door. That way, like, nobody's like, oh, you're not actually going anywhere. Some of those teachers out there, they get like that. A cell membrane operates like a fence. Its job is to be the boundary or the border. It's what marks inside from outside, right? Why polar things do not like going through these spaces. Not so much anymore. We're far enough into the school year that you guys are comfortable doing this, but I bet you, in September, had I asked you to pass amongst a group of seniors, you would have probably been uncomfortable or intimidated. The seniors had been here, they were kind of big, they're kind of scary, now they're just kind of annoying. But, you know, that's because half a year has passed. But if you had to walk through the senior section of the cafeteria by yourself, you likely would have been uncomfortable. Is this true? Think about them. You're like, I still don't like walking in the seniors. That's very much true with anything trying to pass through here. It has to pass through a region of non-polar things. And if you're polar, that's incredibly uncomfortable. You don't want to do it. Chemically, it's unfavorable. Like you're repelled. So instead, if you're polar, you're going to use a large, comfortable passage. You would likely prefer to pass amongst the seniors in the cafeteria if it were a group of you rather than just one of you. There's safety in numbers. Same thing here. Safety in numbers. If they could pass through a carrier protein, not have to deal with that really awkward, uncomfortable part, they'll do so. So that's why it has to be small and non-polar things that go through that region. This very much affects what crosses the cell membrane. You all already have a very good understanding of the chemical principle that allows things to cross the cell membrane. Is when a molecule, or when molecules move from an area of high concentration to low concentration, requires no energy. Happens all by itself. I often compare it to a hill or an inclined plane. If I were to take a ball and put it at the top of my inclined plane, what's going to happen to it? On its own accord, it's going to roll down. Does it by itself. Doesn't require any energy. It's because all of the potential energy that it has, it converts that potential energy into kinetic energy, it rolls down the hill. We call this in chemistry and biology going down the concentration gradient. Going down the concentration gradient from where the concentration is high to where the concentration is low. Quite natural, quite normal. Molecules do this just because it's chemically, kinetically, physically what happens. It does that until it reaches equilibrium. Now, unfortunately for us, Hollister and Abercrombie never give us the opportunity to reach equilibrium. Because on the hour, every hour, they go back out and reintroduce a new concentration gradient by applying more. If they didn't do that, eventually the particles would continue to bounce off of each other until they permeated the entire space that they were able to permeate, and the smell would dissipate, right? It wouldn't be that bad. Like, praise be to God, the mall closes at 9, so from 9 o'clock that night until they open again the next morning and we get reassaulted, they have the opportunity to spread out evenly. When they spread out evenly and there is no longer a concentration gradient, we call that equilibrium. So it's called equilibrium when there is no longer a concentration gradient. Water can freely diffuse across the membrane and does not require a transport protein. It fits in those little spaces between the phospholipids. It's teeny, teeny, tiny, so it just like wiggles through. Osmosis just happens. When we can't fit things through, like we already said, carrier proteins are necessary when things are really big. They're also necessary when things are very polar. So we have to have a transport protein when things are big or things are polar. We call that facilitated diffusion. When they use a carrier protein or a transport protein, we call it facilitated diffusion. It still diffuses. It still doesn't require energy. It still moves from high concentration to low. It needed help from a carrier. That's why we use the term facilitated.
So, what do transport proteins carry through the membrane?
Sometimes glucose, urea, anything that's not small or anything that's polar that has to move across the membrane.
Okay, and they fit in the,
God bless you.
they fit in the little,
In the holes and the, yep.
Can you repeat facilitated diffusion?
Sure. Facilitated diffusion is diffusion, so it moves down the concentration gradient. It requires no energy, but it has to have a carrier protein because it's too big to fit through the phospholipid spaces, or it's polar. Anytime you have molecules that pass through the membrane without using energy, we call it passive transport. So osmosis, diffusion, and facilitated diffusion are all forms of passive transport. So they require no energy at all. It just happens. They're passive. You guys know what it means to be pacifist, right?
Yes.
So to be a pacifist, you're a peace lover. You don't fight, so you're passive. Same thing here. No fight, no energy. It's passive. It just happens.
So osmosis and facilitated diffusion and what else?
Diffusion. Diffusion.
Oh, just
Yep. So let's see if we can't apply this in the simplest example possible. This wonderfully complicated picture is a cell. Inside the cell there are 10 water molecules, and outside the cell there are 2 water molecules. In what direction will water molecules move?
Inside the outside.
From the inside to the outside. Until what? How many will there be on each side?
like 5 on each side.
Add one more. Add one more. 5 on each side, or add the 2 numbers and divide it by 2. Hmm? So until there are 6 water molecules on each side, right? Until there's an equilibrium. What happens to the cell? It was full of water, and then it happens to a water balloon if you let out water.
It's smaller.
Shrinks. So in this instance, this cell would shrink in response to water moving out. When the concentration of solute is higher, we call it hypertonic. And when the concentration is lower, we call it hypotonic. So we can label things as hypertonic, hypotonic, and isotonic. Now the problem with hypertonic and hypotonic, we have to be specific about what we're labeling. I have 3 beakers that have 1 cell each. And in the first set of beakers, or in the first beaker and cell, I have 5% sodium chloride and 5% sodium chloride. Here, we would say that the cell is isotonic to its surrounding. So we call that isotonic. Here, we have 10% inside the cell and 5% outside of the cell. So the cell is hypertonic. The cell is hypertonic. You have to specify which environment you're talking about.
So for the first one, is the cell isotonic?
Mhm. And in the last one, the cell is 5% and its extracellular environment is 10%. So the cell is hypotonic. Now, sodium chloride is charged. It can't freely move across the cell membrane. So what's going to move in response is going to be the water that the sodium chloride is dissolved in. This is where it gets slightly tricky. In the first instance of isotonic, 5% inside, 5% outside, is anything going to move? No, it's already at equilibrium, right? So we say no net movement.